Mars preserves extensive geological and atmospheric evidence that liquid water once existed across its surface. Valley networks, sedimentary deposits, mineralogical signatures, and large scale geomorphology suggest that early Mars may have hosted lakes, rivers, and possibly a northern ocean comparable in scale to Earth's Arctic Ocean. Mars is cold and arid, with most remaining water locked in polar ice caps or buried beneath the surface. This essay examines the evidence for ancient Martian oceans, the mechanisms by which Mars lost much of its atmosphere and surface water, and the ongoing search for subsurface ice and brine reservoirs. It also explores the confirmed transfer of Martian meteorites to Earth and the possibility that early solar system processes allowed planetary material and potentially biological precursors to move between worlds. By comparing Mars's planetary evolution with Earth's ocean systems, this essay considers what the disappearance of Martian oceans reveals about atmospheric protection, magnetic shielding, climate stability, and the delicate planetary conditions required for long-term ocean persistence. Mars provides a natural planetary experiment demonstrating that oceans are not permanent features of rocky worlds. Geological and atmospheric evidence indicates that Mars once possessed substantial surface water, possibly including a northern ocean comparable in scale to Earth's Arctic Ocean. The subsequent loss of its magnetic field and atmosphere allowed solar radiation and atmospheric escape processes to gradually remove much of this water. Studying how Mars lost its oceans offers insight into the planetary conditions that allow oceans to persist, conditions that remain essential for the long-term stability of Earth's own ocean systems. Mars is often imagined as a dry, barren desert. Images returned by orbiters and rovers show a world of dust plains, impact craters, and thin atmosphere. The planet's present surface is cold, oxidized, and largely devoid of liquid water. Yet this modern image tells only part of Mars's story. Across the Martian landscape lie geological features that reveal a very different past, one in which liquid water once moved across the planet on a planetary scale. Ancient river valleys cut through the cratered highlands like the dry skeletons of terrestrial drainage systems. Impact basins preserve delta deposits where rivers once delivered sediment into standing bodies of water. Orbital spectrometers have identified minerals that form only through prolonged interaction between water and rock. Together, these features provide compelling evidence that early Mars was not merely damp in isolated places. It was a world shaped by flowing water. Across Mars, we see clear traces of that ancient hydrology: river valleys, lake basins, sediment deltas, mineral deposits that form only in water. These features appear across large portions of the planet, especially in terrains dating to the Noachian period more than 3.7 billion years ago. Their distribution suggests that water once flowed repeatedly across the Martian surface, rather than appearing only during rare or catastrophic events. Billions of years ago, Mars may therefore have looked far more like Earth than it does today. Geological evidence suggests that early Mars possessed a thicker atmosphere, active volcanism, and surface temperatures capable of supporting liquid water. Under those conditions, precipitation and surface runoff may have sustained rivers and lakes across large portions of the planet. Some planetary models suggest that the northern hemisphere once held a particularly large body of water. The planet's northern lowlands form a vast basin that covers nearly half the Martian surface, and several researchers have proposed that this basin may once have contained an ocean, sometimes referred to as Oceanus Borealis. If that interpretation is correct, Mars was once a world where rivers flowed downhill toward a northern basin, lakes accumulated in impact craters and depressions, and perhaps even oceans spread across entire planetary basins. Estimates suggest that the total water inventory of early Mars may have been sufficient to cover the planet with a global layer hundreds of meters deep if evenly distributed. That possibility changes how scientists think about the planet. Mars is not simply a dry world that never had water. It is a world that appears to have possessed significant surface water early in its history, and then gradually lost it. The surface features we observe today therefore represent more than isolated curiosities. They are fragments of a larger planetary story, one in which a world capable of sustaining rivers and lakes eventually transformed into the frozen desert we see today. Understanding how that transformation occurred has become one of the central questions of planetary science. Mars, in other words, is not only a dry planet, it is a planet that remembers water. The idea that Mars once held an ocean is not based on a single dramatic image or one isolated measurement. It emerges from the convergence of multiple lines of evidence: large-scale topography, sedimentary landforms, valley network geometry, and basin-scale patterns that make more sense in the presence of long-lived standing water than in its absence. Taken together, these features suggest that early Mars may not merely have been wet in scattered places, but may have supported a hydrological system large enough to move water across the planet and accumulate it within a northern basin. The most important geographic feature in this discussion is the stark contrast between the ancient southern highlands and the lower northern plains. Mars is divided by what planetary scientists often describe as a crustal dichotomy. The southern hemisphere is older, more heavily cratered, and topographically elevated, while much of the northern hemisphere is lower, smoother, and basin-like in structure. That contrast invites a simple but consequential question. If water once flowed across early Mars, where would it have gone? The most obvious answer is downhill, into the north. That inference became more compelling as orbital mapping improved. Researchers identified shoreline-like transitions between highlands and lowlands, possible coastal contacts, and basin margin features in the northern plains that some interpreted as remnants of an ancient ocean boundary. These interpretations remain debated in their finer details, partly because Mars has undergone billions of years of resurfacing, impact gardening, tectonic modification, and sediment redistribution. But debate over the exact geometry of a proposed shoreline is not the same as an absence of oceanic evidence. On the contrary, the broader pattern has continued to support the possibility that a large body of water once occupied the northern lowlands, even if its exact margins shifted through time or were later obscured. One of the strongest arguments comes not from putative shorelines alone, but from the river systems that appear to feed them. Ancient valley networks branch across the southern highlands in patterns that closely resemble terrestrial drainage basins shaped by sustained runoff. These are not random grooves or isolated channels. They are integrated systems, with tributaries joining larger trunk valleys in ways that suggest repeated movement of water downhill across the landscape. Their geometry implies that water was not merely erupting from underground in scattered bursts. At least in many regions and times, it was cycling through the atmosphere, condensing, precipitating, and then flowing over land. That is why the ocean question cannot be separated from the hydrological one. If rivers carved the highlands, and if those rivers drained toward long-lived standing bodies of water, then early Mars may once have supported an active hydrological cycle involving evaporation, atmospheric water vapour, precipitation as rain or snow, runoff through river systems, and the accumulation of water in lakes and larger basin-scale reservoirs. In that sense, the proposed Northern Ocean is not simply a large pool left behind by melting. It is the likely receiving basin in a larger planetary water system. The scale of that system matters. Some estimates suggest that early Mars may have contained enough water to cover the planet with a global equivalent layer roughly 100 to 500 meters deep if evenly distributed, with the northern basin acting as the principal reservoir. That range does not describe a minor wet episode. It implies a water inventory large enough to influence climate, surface chemistry, erosion, sediment transport, and the long-term evolution of the crust. This is one reason why ancient delta deposits are so important. Deltas form where flowing water enters standing water and drops its sediment load. Their presence therefore implies not only rivers, but basins capable of holding water long enough for sediment to be sorted, deposited, and preserved. Jezero crater provides one of the clearest examples. Although not part of the Northern Ocean basin itself, it preserves a remarkably distinct delta formed where an ancient river entered a standing lake. Such deposits are among the strongest indicators that Mars once sustained persistent bodies of water rather than only transient floods. The same logic applies to open basin lakes more broadly. Researchers have identified Martian basins that appear to have both inflow and outflow channels, implying that water not only collected there, but rose high enough to spill over and continue moving downslope. Such systems are difficult to explain without repeated or sustained hydrological input. In a world shaped only by isolated melt events, one might expect temporary ponding. In a world with runoff, lake overflow, and connected drainage, one begins to see something more integrated. What emerges from all of this is not absolute certainty about every contour of an ancient Martian coastline. It is something more scientifically durable, a coherent picture in which topography, sedimentary processes, valley networks, and basin geometry all point toward a Mars that was once hydrologically active and capable of supporting large, standing bodies of water, perhaps including a northern ocean of major planetary significance. And once that picture is taken seriously, the next question follows naturally. If early Mars really did support rivers, lakes, and perhaps an ocean in the north, what traces should that water have left behind in the rocks themselves? Orbital observations and rover missions reveal widespread evidence that liquid water once interacted with the Martian surface. This evidence does not rest on a single type of feature. It appears across the landscape in multiple forms: valley networks carved by runoff, delta deposits laid down in standing lakes, and minerals that form only when water alters rock over time. Taken together, these lines of evidence strengthen the case that early Mars was not merely damp in isolated places, but geologically shaped by water on a significant scale. Among the clearest signs of past liquid water are the ancient valley networks that branch across the Martian highlands. These systems resemble terrestrial river basins in both pattern and structure. Tributaries join larger channels in organised drainage networks, suggesting sustained surface runoff rather than random fracturing or isolated collapse features. Their importance lies in what they imply. Branching drainage systems are difficult to explain without repeated movement of water over the surface. In many regions, the geometry of these valleys suggests that water once flowed downhill across the landscape in ways consistent with precipitation, runoff, and erosion over extended periods of time. This does not mean every Martian valley formed in exactly the same way. Some may reflect groundwater sapping, transient melting, or local hydrological conditions. But taken collectively, the global distribution and integrated structure of the valley networks strongly support the conclusion that surface water once played a central role in shaping the early Martian landscape. If valley networks record water in motion, delta deposits record water arriving somewhere. Locations such as Jezero Crater preserve ancient deltas where rivers once flowed into standing lakes. These deposits are especially important because deltas require more than channel flow alone. They form when water carrying sediment slows as it enters a relatively stable body of standing water, causing that sediment to settle out in layered accumulations. Their presence therefore implies not only runoff, but lakes that persisted long enough to receive, sort, and preserve those materials. Jezero Crater has become especially significant for this reason. Its preserved delta records an environment in which flowing water and a long-lived lake interacted over time, creating one of the most promising sites on Mars for studying ancient habitability. Because deltas on Earth can trap fine sediments, organics, and biosignatures, their Martian equivalents are considered high-value targets for astrobiological investigation. More broadly, researchers have identified open basin lakes elsewhere on Mars that appear to have both inlet and outlet channels. These systems suggest that water not only collected in basins, but sometimes accumulated to the point of overflow, implying repeated hydrological input rather than a single transient event. The geological case for ancient water is strengthened further by the mineral record. Spectroscopic observations from orbit have identified minerals that form only in water-rich environments, including clays, sulfates, hydrated silica. These minerals are crucial because they record water-rock interaction directly. Unlike channels or basins, which can sometimes be debated in geomorphic terms, hydrated minerals preserve chemical evidence that liquid water once altered the crust. Clay minerals, or phyllosilicates, are particularly important. They form when water chemically alters volcanic or basaltic rock over extended timescales. Their presence across ancient terrains suggests that early Martian environments included persistent aqueous conditions, in some cases likely involving relatively neutral water chemistry rather than only short-lived acidic episodes. Sulfates tell a complementary story. These minerals often form when water evaporates and leaves dissolved salts behind, indicating environments where standing water may have concentrated and then retreated. Hydrated silica can point to hydrothermal or volcanic water interactions, suggesting that some Martian aqueous environments may have involved heated crustal systems as well. These mineral signatures indicate prolonged chemical interaction between water and rock. They also suggest that ancient Mars hosted more than one type of watery environment. Water likely existed as surface runoff, standing lakes, evaporative basins, and perhaps subsurface hydrothermal systems at different times and in different places. Taken together, the geological evidence presents a coherent picture. Valley networks suggest sustained runoff. Delta deposits indicate standing lakes. Water-formed minerals preserve the chemical record of prolonged aqueous alteration. None of these lines of evidence alone proves the existence of a northern ocean, but together they show that early Mars was a world where liquid water was active, persistent, and geologically transformative. That conclusion creates a deeper problem. If Mars once possessed the conditions necessary for rivers, lakes, and extensive water-rock interaction, then the planet itself must once have been very different from the cold, thin-aired world we see today. To understand how Mars could once support so much liquid water, we must look beyond the rocks and ask what kind of planetary environment made that water possible. The geological evidence described so far, valley networks, delta deposits, lake basins, and water-formed minerals, all points toward a basic conclusion. Early Mars must once have been capable of sustaining liquid water at or near its surface. Yet under the conditions observed on Mars today, such stability would be extremely difficult. The modern planet has a thin atmosphere, low surface pressure, and temperatures that often keep water frozen or cause it to sublimate directly into vapour. For rivers and lakes to have existed in the past, Mars must once have been a significantly different world. Most evidence for surface water dates to the Noachian period, approximately 4.1 to 3.7 billion years ago. This era corresponds to the earliest major phase of Martian geological history, when the crust was heavily cratered but also more geologically active than it is today. During this time, Mars likely possessed several conditions favourable to liquid water: a thicker atmosphere, active volcanism, a global magnetic field, temperatures capable, at least intermittently, of supporting liquid water at the surface. These conditions would have made early Mars far more hospitable to water than the planet we observe now. A thicker atmosphere is especially important because atmospheric pressure strongly affects the stability of liquid water. On modern Mars, surface pressure is so low that liquid water is generally unstable. But if early Mars possessed a denser atmosphere, dominated in part by carbon dioxide, greenhouse warming could have raised temperatures enough for water to remain liquid for longer periods, at least regionally or episodically. Volcanic outgassing likely played a central role in this process by releasing carbon dioxide and other gases into the atmosphere, temporarily thickening it and enhancing surface warming. This does not mean that early Mars was necessarily warm in the same way Earth is warm. The exact climate of Noachian Mars remains debated. Some models favour a relatively warm and wet world with rainfall and sustained runoff, while others describe a colder planet punctuated by episodic warming, snowmelt, or transient hydrological activity driven by impacts, volcanic events, or orbital variations. But despite those differences, the geological record itself makes one point difficult to avoid. Liquid water interacted with the surface often enough and for long enough to carve valleys, deposit deltas, alter minerals, and shape basins. Another important part of this early environment was the likely presence of a global magnetic field. On Earth, the geomagnetic field is generated by motion within the liquid outer core. That motion creates a planetary dynamo, producing a magnetic field that extends outward and helps shield the atmosphere from direct erosion by the solar wind. Early Mars appears to have possessed a similar dynamo. Evidence for this comes from magnetized crustal rocks, which preserve traces of ancient magnetic alignment and suggest that Mars once maintained a global magnetic field early in its history. That magnetic field mattered because it helped protect the atmosphere. Without magnetic shielding, charged particles from the Sun can more readily interact with the upper atmosphere and strip gases away over time. With a functioning magnetic field, a thicker atmosphere, and continuing volcanic outgassing, early Mars may have been able to maintain the surface pressure and thermal conditions needed for liquid water to exist, at least intermittently, across large areas. This combination of conditions helps explain why early Mars could once support rivers, lakes, and perhaps a northern ocean. But the geological record also shows that this environment did not last indefinitely. By the beginning of the Hesperian period, signs of widespread surface water appear to become less common. Atmospheric loss seems to have accelerated. The climate grew colder and drier. Surface water became less stable, and the hydrological system that once shaped the planet began to break down. Something fundamental had changed in the planetary system. To understand how Mars went from a world capable of supporting liquid water to the cold, arid planet we see today, we have to move from climate and surface geology to a deeper question. How did Mars begin to lose the atmospheric and magnetic protections that once made its oceans possible? Mars did not simply dry out. The disappearance of its surface water appears to be tied to deeper planetary changes that gradually altered the conditions necessary for oceans to persist. One of the most important transitions in Martian history was the loss of its global magnetic field. Early in its evolution, Mars likely possessed a magnetic dynamo similar to Earth's. On Earth, movement within the liquid outer core generates a magnetic field that extends outward into space, forming a protective magnetosphere. This magnetic shield deflects much of the solar wind, the continuous stream of charged particles flowing outward from the Sun, helping to protect Earth's atmosphere from being stripped away over time. Evidence preserved in magnetized regions of the Martian crust suggests that Mars once maintained a comparable magnetic field early in its history. But unlike Earth, Mars is significantly smaller. Smaller planets tend to lose internal heat more quickly, and as Mars cooled, convection within its interior likely weakened. As a result, the dynamo responsible for generating the magnetic field gradually shut down. Once Mars lost its global magnetic shielding, the solar wind could interact much more directly with the planet's upper atmosphere. Over long periods of time, these interactions slowly removed atmospheric gases. Charged particles from the solar wind can transfer energy to atmospheric molecules, allowing them to escape the planet's gravitational pull. Without a strong magnetic field to deflect much of this solar activity, Mars became increasingly vulnerable to atmospheric erosion. As the atmosphere thinned, the consequences for surface water became increasingly severe. Liquid water requires a certain range of temperature and pressure to remain stable. If atmospheric pressure falls too low, water can no longer remain liquid at the surface for extended periods. Instead, it freezes or sublimates directly into vapor. The gradual loss of atmospheric pressure therefore destabilized the hydrological conditions that once allowed rivers, lakes, and perhaps oceans to exist. Over geological time, Mars transitioned from a planet capable of supporting persistent surface water to one where liquid water became increasingly rare and short-lived. This transformation did not occur all at once. It unfolded over hundreds of millions of years as the atmosphere slowly escaped to space and the planet cooled further. Today, Mars retains only a thin atmosphere, composed primarily of carbon dioxide, with a surface pressure less than 1% of Earth's. Although the oceans themselves are gone, the processes responsible for their disappearance are still measurable. NASA's MAVEN, the Mars Atmosphere and Volatile Evolution mission, launched in 2013, studies how solar wind and radiation continue to strip atmospheric particles away from Mars even today. The loss of Mars's magnetic field therefore set off a chain of planetary consequences: atmospheric erosion, declining surface pressure, falling temperatures, and the gradual destabilization of liquid water at the surface. Understanding these changes helps explain how a planet that once preserved river valleys, lake basins, and mineral evidence of water could eventually become the cold, arid world we observe today. Water does not simply float away from a planet. For an ocean to be lost to space, the process must occur in stages, moving water from the surface into the atmosphere and then breaking it apart at high altitude. On Mars, this sequence appears to have unfolded slowly over immense spans of time as the atmosphere thinned and the planet lost its ability to protect volatile molecules from solar radiation and atmospheric escape. The first step is evaporation. When liquid water is present at the surface, some fraction of it enters the atmosphere as water vapour. On early Mars, rivers, lakes, and possible oceanic basins would have contributed water vapour to the air through evaporation, just as Earth's oceans do today. If Mars once supported an active hydrological cycle, then atmospheric water vapour would have been a normal part of that system. The second step is the movement of water vapour upward. Once in the atmosphere, water vapour can rise into higher layers. On a planet with a stable, dense atmosphere, much of that vapour remains part of a cycling system of condensation and precipitation. But on Mars, as atmospheric pressure declined and the upper atmosphere became increasingly exposed to solar radiation, water molecules reaching high altitudes became more vulnerable to being broken apart. That leads to the third step: photodissociation. Ultraviolet radiation from the sun can split water molecules into their component atoms, hydrogen and oxygen. This process is especially important in the upper atmosphere, where solar radiation is intense and atmospheric shielding is limited. Once water molecules are broken apart, their components no longer behave the same way. The fourth step is hydrogen escape. Hydrogen is extremely light. Once freed from a water molecule, it can escape a planet's gravitational pull much more easily than heavier atoms can. Over millions and billions of years, this means that a significant amount of a planet's water inventory can be lost atom by atom as hydrogen drifts off into space. In simplified form, the process looks like this. Liquid water evaporates. Water vapour rises into the upper atmosphere. Ultraviolet radiation splits water molecules apart. Hydrogen atoms escape into space. This sequence is slow on human timescales, but profound on geological ones. Over long periods, repeated loss of hydrogen steadily removes water from the planet's active system. It does not require a single catastrophic event. Instead, it acts as a persistent leak, gradually reducing the total amount of water available to cycle between surface, atmosphere, and ice. In this way, a world that once supported substantial bodies of liquid water can be transformed into one where only remnants remain. The oxygen left behind does not usually escape as easily. Some oxygen is also lost to space through other atmospheric processes, but much of it reacts with the surface. On Mars, that oxygen has helped oxidize iron-bearing minerals, producing iron oxides that contribute to the planet's distinctive reddish colour. In that sense, the modern appearance of Mars is chemically tied to the breakdown of ancient water. Part of the planet's red surface is, quite literally, a residue of long-term oxidation associated with water loss. This is what makes Mars such a powerful planetary case study. Its oceans, if they once existed on the scale many models suggest, did not disappear all at once. They were gradually dismantled by a chain of physical processes that moved water from the surface into the atmosphere, from molecules into atoms, and from atoms into space. The result was not only a drier planet, it was a world in which the water system itself became progressively harder to sustain. One of the strongest lines of evidence that Mars lost large amounts of water over time comes not from its valleys or mineral deposits, but from the chemistry of its atmosphere. Scientists can study the history of planetary water loss by examining hydrogen isotopes. Hydrogen exists in two main forms: ordinary hydrogen, deuterium, a heavier isotope containing an additional neutron. This distinction matters because lighter atoms escape a planet's gravity more easily than heavier ones. When water molecules in the upper atmosphere are broken apart and hydrogen begins to escape into space, ordinary hydrogen is lost more readily than deuterium. Over long periods of time, the remaining water and atmospheric hydrogen become progressively enriched in the heavier isotope. This means that the deuterium to hydrogen ratio acts as a kind of planetary fingerprint. If Mars had lost only a small amount of water, its isotopic ratio would remain closer to the baseline expected for a water-rich world in the early solar system. But if Mars lost a substantial fraction of its original water inventory, the atmosphere would show a much higher proportion of deuterium relative to ordinary hydrogen. That is exactly what scientists observe. Measurements of the Martian atmosphere show a strongly elevated deuterium to hydrogen ratio compared with Earth's oceans, and with values expected for primordial water. This enrichment indicates that large amounts of the lighter hydrogen have already escaped into space, leaving the heavier isotope behind in greater relative abundance. In practical terms, this is one of the clearest chemical indicators that Mars once possessed much more water than it does today. The isotopic evidence is especially important because it complements the geological record. Valley networks, lake basins, and water-formed minerals show that water once existed at the surface. The atmospheric isotope record helps explain what happened afterward. It provides independent support for the conclusion that Mars did not merely freeze its water in place. A substantial fraction of that water was ultimately lost through atmospheric escape. This evidence also helps scientists estimate the scale of that loss. Although exact reconstructions vary depending on the model and assumptions used, the elevated deuterium to hydrogen ratio suggests that early Mars once held significantly more water than is visible in its present ice caps and subsurface reservoirs alone. In other words, the atmosphere preserves a chemical memory of vanished water, just as the surface preserves a geological one. The significance of this is difficult to overstate. Mars's modern appearance might suggest a planet that was always dry, always cold, and always hostile to surface water. But the isotopic evidence argues otherwise. It indicates a world that once held a larger water inventory and then lost much of it gradually, selectively, and irreversibly over geological time. That conclusion brings the argument to an important transition. If the atmosphere preserves evidence of vanished water, the next question is obvious. How much water remains on Mars today, and where is it now stored? Despite its dry appearance, Mars still holds significant water reserves. The difference is that this water no longer exists primarily as flowing rivers, open lakes, or surface oceans. Instead, much of the remaining Martian water is locked away as ice, concentrated at the poles, buried beneath dust and sediment, and preserved in frozen reservoirs below the surface. In that sense, Mars is not a world entirely emptied of water. It is a world where much of the surviving water has been displaced from the active surface system into storage. The most obvious reservoirs are the polar ice caps. Both the North and South poles contain thick, layered deposits of water ice mixed with seasonal or permanent carbon dioxide ice. These polar caps preserve a substantial fraction of the planet's remaining near-surface water inventory. If the water ice stored there were melted and distributed globally, it could cover the planet with a layer of water tens of meters deep. That is far less than the water volumes inferred for ancient Mars, but it is still a meaningful quantity. The modern planet may be arid, but it is not waterless. These polar deposits are also scientifically valuable because they record climate history. Layered accumulations of ice and dust preserve evidence of changing obliquity, seasonal cycling, and long-term environmental variation. In this sense, the polar caps function not only as frozen reservoirs, but as climatic archives, recording how Mars has changed as it cooled and dried over time. Beyond the poles, radar observations have revealed additional stores of subsurface ice. Instruments such as SHARAD have detected buried glaciers, underground ice sheets, and ice-rich materials extending into the mid-latitudes. These findings are important because they show that Martian water is not confined to the poles alone. Significant quantities remain hidden beneath the surface in regions where local temperatures and pressures allow ice to persist under protective layers of dust and sediment. Some of these buried deposits appear to preserve ice in forms that resemble terrestrial glacial remnants covered by debris. Others may represent ancient climatic redistribution, recording periods when ice migrated away from the poles during different phases of Martian axial tilt. Whatever their exact origin, these subsurface reservoirs represent a major part of Mars's remaining water inventory and demonstrate that the history of Martian water did not end simply because surface rivers disappeared. This distinction matters. When people imagine Mars as dry, they often imagine a planet almost completely stripped of water. But the scientific picture is more complex. Mars has indeed lost a large amount of water over time, as indicated by isotopic evidence and atmospheric escape studies. Yet some fraction of that water was not lost to space. It was retained, frozen, buried, and geologically redistributed across the planet. That makes modern Mars, in a limited sense, a world of hidden water. Not hidden in the way ocean worlds such as Europa or Enceladus are believed to conceal global liquid oceans beneath ice shells, but hidden in the sense that much of Mars's remaining water survives in forms not immediately visible from the surface. The planet still preserves water as a physical resource, even if that water no longer participates in an active surface hydrological cycle. This also means that the story of Martian water is not only a story of disappearance, it is also a story of transformation. Some water escaped into space. Some became chemically bound into minerals. Some froze into polar layered deposits. Some persisted underground as buried ice. The modern Martian landscape is therefore not the end point of a single process, but the cumulative result of several: atmospheric loss, climatic cooling, geologic storage, and the freezing of what remained. That raises a further question. If buried ice and polar reservoirs still survive on Mars today, could any part of that surviving water remain liquid under the right conditions? Perhaps as cold brines trapped beneath thick ice. That possibility leads directly to one of the most intriguing and controversial questions in modern Mars science. If Mars still preserves large quantities of water as buried ice and polar deposits, the next scientific question is whether any of that surviving water might remain liquid under the right conditions. This possibility has drawn particular attention at the South Polar ice cap, where radar observations have detected unusually bright reflections beneath thick layered ice deposits. Some researchers have interpreted these reflections as signals consistent with liquid brines trapped beneath the ice. Extremely cold, salty water reservoirs that remain liquid because dissolved salts lower the freezing point. If that interpretation is correct, the implications are significant. These environments would not resemble open lakes or oceans at the surface. They would be isolated, pressurized, deeply buried, and extraordinarily cold. In other words, they would be among the most difficult aquatic environments in the solar system to access directly. But they would also represent one of the clearest examples of present-day liquid water stability on Mars, even if only in small, localized, and highly saline form. The evidence remains debated. Radar sounding of planetary ice is complex, and bright reflections can sometimes arise from contrasts in layering, mineral composition, or unusual ice properties rather than liquid water itself. Because of that, the case for subglacial lakes on Mars is not yet settled. Some scientists view the radar signatures as strong candidates for liquid brines, while others argue that alternative explanations remain plausible. At present, the correct scientific posture is cautious. The South Polar radar reflections are intriguing and important, but not yet universally accepted as definitive proof of subglacial lakes. Even so, the question matters because the possible environments are conceptually familiar. On Earth, subglacial lakes beneath Antarctica provide a striking analogue. These lakes are sealed beneath kilometres of ice, cut off from sunlight and exposed to immense pressure. For a long time, such environments seemed too isolated and too extreme to support meaningful biological activity. Yet research on Antarctic subglacial systems has shown that microbial life can persist in dark, cold, nutrient-limited environments beneath ice sheets. That comparison does not prove that Mars hosts life. But it does change the question. If microbial ecosystems on Earth can survive beneath Antarctic ice in darkness and near isolation, then similar environments on Mars, if liquid brines truly exist there, become scientifically important not only as hydrological curiosities, but as potential habitat analogues. They would represent places where water, chemistry, shielding from radiation, and long-term environmental stability might coincide in ways relevant to astrobiology. This is one reason Antarctica has mattered so much throughout the larger ocean series. Antarctica demonstrates that oceans and lake-like water systems do not have to be open to the sky to remain scientifically and biologically important. Water can persist beneath ice, in darkness, outside ordinary human expectations. Mars raises the possibility, still uncertain but scientifically compelling, that something similar may occur there as well. In that sense, possible Martian subglacial lakes occupy an important middle ground in the story of water on Mars. They are not evidence that Mars retained its ancient oceans intact, nor are they evidence that the planet is entirely dry. Instead, they suggest that the history of Martian water may include not only loss and freezing, but localized persistence, small pockets where water may still survive in altered form beneath the ice. And if water can survive there, even under extreme conditions, the next question becomes broader still. How isolated is Mars really from the rest of the solar system and from Earth itself? Mars and Earth are not completely isolated planetary systems. In the early solar system, and even today on much rarer timescales, large impacts can launch rock from one world into space and send it across interplanetary distances. This process is not speculative. It has already been confirmed through the study of Martian meteorites found on Earth. When a large asteroid strikes Mars with sufficient force, some fragments of Martian crust can be ejected at velocities high enough to escape the planet's gravity. A small fraction of that debris then enters solar orbit. Over time, some of those fragments cross Earth's path and survive atmospheric entry, eventually landing at the surface as meteorites. Scientists identify these rocks as Martian not by guesswork, but through geochemical and isotopic evidence. Some contain trapped gases whose composition closely matches the Martian atmosphere measured by spacecraft. Others preserve mineralogical and age patterns consistent with known Martian crustal materials. Together, these signatures confirm that material has indeed travelled naturally from Mars to Earth. More than 300 Martian meteorites have now been identified. That number alone is scientifically important because it demonstrates that planetary exchange is not a theoretical edge case. It is a real process operating within the solar system. This fact changes the way Mars is understood. Mars is often imagined as distant, separate, and observationally inaccessible, except through orbiters and rovers. But in a material sense, part of Mars has already arrived here. Pieces of its crust are sitting in terrestrial collections and laboratories, where they can be studied with tools far more sophisticated than anything currently flown on robotic spacecraft. That has made Martian meteorites one of the earliest and most important sources of direct physical evidence about Mars. Before modern rovers began drilling and analysing rocks in place, meteorites provided scientists with samples of Martian volcanic history, crustal chemistry, shock processes, and environmental alteration. They helped establish timelines for igneous activity, surface exposure, and geologic evolution on the planet. They also matter because they make the transfer of matter between planets concrete rather than abstract. Mars and Earth do not merely resemble one another as rocky planets in the inner solar system. They have, in a limited but real sense, exchanged material. That exchange links planetary histories in a way that is easy to overlook when thinking about worlds as sealed spheres moving independently through space. This is one reason the future Mars sample return effort is so significant. Unlike naturally ejected meteorites, which arrive after violent impacts and long exposure histories, returned samples from missions such as Perseverance would be carefully selected and geologically contextualized. The Perseverance rover is already collecting and caching rock cores from Jezero crater for possible return to Earth in a future campaign, allowing scientists to analyze sedimentary and igneous materials in laboratories with far greater precision than rover-based instruments allow. That distinction matters because context is everything in geology. A meteorite tells scientists that a rock came from Mars. A return sample could tell them where on Mars it came from, what environment it formed in, what other rocks surrounded it, and whether it preserves signs of aqueous alteration or even possible biosignatures. In that sense, meteorites and sample return belong to the same larger story. Both remind us that Mars is not beyond reach. Its history is not locked away forever on another planet. Some of its material has already crossed the distance to Earth naturally. More may do so intentionally through future exploration. And once that fact is accepted, another question follows almost inevitably. If rock can move between planets, could something else have travelled with it? The confirmed exchange of rocks between Mars and Earth raises a more provocative scientific question. If rock can move between planets, could microbial life, or at least biological material, travel with it? This possibility is known as lithopanspermia. The idea does not claim that life definitely came to Earth from Mars, nor does it require a dramatic science fiction scenario. It proposes something narrower and more scientifically testable, that microorganisms protected inside rock fragments could, in principle, survive a sequence of extreme events involving impact ejection, travel through space, and eventual atmospheric entry onto another world. The logic begins with what is already known. Large impacts can eject crustal material from Mars into interplanetary space. Some of that material reaches Earth as Martian meteorites. If those rocks were launched from environments that once hosted microbial life, perhaps subsurface water systems, sedimentary deposits, or hydrothermally altered crust, then the question is whether any organisms inside them could endure the journey. At first glance, the answer might seem obviously no. Impact ejection is violent. Space is cold, airless, and filled with radiation. Atmospheric entry generates heat and shock. Each step appears hostile to life. Yet, the issue is more complex when considered at microbial scale. Organisms shielded inside rock are not exposed in the same way as material on the surface. Laboratory studies and theoretical models suggest that some microorganisms, especially hardy spores or extremophiles, can survive combinations of shock pressure, vacuum exposure, radiation, and extreme temperature if adequately protected by surrounding mineral material. This does not make lithopanspermia proven. It makes it physically plausible enough to remain scientifically interesting. That distinction matters. There is currently no evidence that life on Earth originated on Mars. There is also no confirmed evidence that Mars ever hosted life at all. The hypothesis remains speculative in its biological implications, but it is grounded in a real physical mechanism. Planetary material does move between worlds, and microbial survival under extreme conditions is more robust than once assumed. In that sense, lithopanspermia occupies an unusual place in astrobiology. It is not a claim about aliens, it is a question about continuity within a shared planetary system. The early solar system was more violent than the present one. Large impacts were more common, and planetary surfaces exchanged debris more readily. If microbial life emerged early on one world, while neighbouring worlds still possessed surface water or habitable subsurface environments, then biological material might have been transported between them as part of ordinary impact dynamics. Mars is especially relevant here because early Mars may have been habitable at a very ancient time, possibly during or before the period when life was emerging on Earth. If Mars once hosted lakes, groundwater systems, hydrothermal environments, or perhaps even an ocean, then it may have possessed settings in which simple life could have arisen or persisted. If impacts then ejected crustal material from such environments, some portion of that material could, at least in theory, have reached Earth. That possibility does not prove a Martian origin for terrestrial life, but it does widen the conceptual frame. Instead of treating each planet as a sealed biological experiment, lithopanspermia suggests that early planetary environments may have been more connected than they now appear. Earth and Mars may have exchanged not only rocks, but potentially prebiotic chemistry, or even microbial passengers if life existed early enough and conditions allowed survival. This is one reason Mars remains so important in the search for past life. If Mars never hosted life, that result would still be scientifically profound. It would suggest that even with water, volcanism, and potentially habitable conditions, life may be rarer or more contingent than hoped. But if Mars did host life, even simple microbial life, then the implications would be enormous. It would mean that life emerged at least twice in one solar system, or that biological continuity between worlds is more possible than once imagined. Either conclusion would reshape how we think about oceans, habitability, and the distribution of life in the universe. And that brings the essay to a broader planetary comparison. Mars is not the only world associated with water. It is one among several ocean worlds, but it may represent a very different category from the others. The solar system contains several kinds of ocean worlds. Earth is the most familiar example, a planet with extensive surface oceans that interact continuously with the atmosphere, climate system, and biosphere. Europa and Enceladus appear to represent a very different type. Worlds where oceans may persist beneath thick shells of ice, hidden from direct view but sustained by internal heat and protected from space by overlying frozen crust. Antarctica, though not a separate planet, offers a powerful terrestrial analogue for such environments. Beneath its ice sheet lie subglacial lakes and water systems isolated from sunlight, yet still scientifically and biologically significant. Mars belongs to another category. It is not best understood as a world with open oceans today, nor as one confidently known to preserve a global subsurface ocean beneath an icy shell. Instead, Mars appears to represent a world that once possessed substantial surface water, perhaps including lakes, river systems, and a northern ocean, and then gradually lost the planetary conditions required to sustain that water over time. That distinction makes Mars especially important in comparative planetology. Earth shows what it looks like when oceans persist. Europa and Enceladus suggest that oceans may endure even when buried beneath ice. Antarctica demonstrates that water systems can remain hidden, cold, dark, and still scientifically alive with possibility. Mars, by contrast, may show what happens when a planet crosses the threshold in the other direction, when an ocean-bearing world loses atmospheric thickness, magnetic shielding, and long-term climatic stability, and water is redistributed into ice, minerals, and space. In that sense, Mars is not simply another ocean world. It is a former ocean world, or perhaps more precisely, a world that preserves the geological memory of oceanic conditions after those conditions largely ceased to exist. That makes it an essential comparison point. If scientists want to understand how oceans begin, evolve, and disappear, they need more than one example. Earth alone cannot answer the full question, because its oceans are still here. Europa and Enceladus may eventually help answer how oceans survive beneath ice. Mars adds the missing contrast, a nearby rocky world where water once shaped the landscape extensively, but where the active surface ocean system no longer survives. This comparison sharpens the broader theme of the series. Water is not a single phenomenon repeating identically across worlds. Oceans can exist in radically different planetary contexts, exposed at the surface, as on Earth, hidden beneath ice, as on Europa and Enceladus, sealed within subglacial systems, as in Antarctica, or preserved only in geological memory, as on Mars. Seen this way, Mars is not an outlier, but part of a larger continuum. It reminds us that oceans are dynamic outcomes of planetary history, not permanent guarantees. Some worlds keep them, some conceal them, some lose them. And because Mars is close enough to study in detail, it gives planetary science something extraordinarily valuable. Not merely a dry planet, but a record of what a once water-rich world can become when the systems supporting long-term ocean persistence fall out of balance. That is why Mars belongs among the ocean worlds. Not because it still resembles them in the present tense, but because understanding how it changed helps clarify what oceans really are. Contingent, evolving features of planetary systems, shaped by atmosphere, heat, chemistry, geology, and time. Mars demonstrates that oceans on rocky planets depend on a delicate combination of planetary conditions. Surface water requires more than the presence of ice or minerals. It depends on a stable set of planetary systems working together over immense spans of time. Several factors appear especially important. Atmospheric pressure sufficient to allow liquid water to remain stable at the surface. Magnetic shielding that protects the atmosphere from direct erosion by the solar wind. Long-term climate stability, influenced by volcanic outgassing, greenhouse gases, and planetary energy balance. Geological processes that recycle atmospheric gases and regulate planetary chemistry. On early Mars, many of these conditions may once have existed. Geological evidence suggests that the planet possessed a thicker atmosphere, active volcanism, and surface environments capable of sustaining liquid water. Over time, however, Mars lost its global magnetic field. Without that protection, the solar wind was able to interact directly with the atmosphere, gradually stripping away gases that once helped maintain surface pressure and temperature. As the atmosphere thinned, the stability of liquid water declined. Some water escaped to space through atmospheric processes. Some became locked within minerals. Much of what remained eventually froze into ice deposits at the poles or within the subsurface. This transformation unfolded over billions of years, driven by planetary-scale physical processes. Earth presents a different kind of fragility. Our planet still retains a strong magnetic field, a dense atmosphere, and active geological cycles that help stabilize climate and ocean chemistry. At the planetary level, these systems continue to support persistent oceans. Yet, the stability of Earth's ocean ecosystems is now being altered on much shorter timescales through human activity. Ocean warming, acidification, deoxygenation, and biodiversity loss are reshaping marine environments within decades rather than geological epochs. While these processes do not threaten the existence of oceans themselves in the way that atmospheric escape reshaped Mars, they do affect the biological systems that oceans support. In that sense, the comparison between Earth and Mars highlights two different kinds of planetary vulnerability. Mars demonstrates that oceans can disappear when the physical systems supporting them collapse. Earth shows that oceans can remain physically present while their ecological systems change rapidly under external pressures. Understanding how oceans disappear on planetary timescales, therefore, deepens our appreciation of how easily ocean systems can be disrupted on much shorter ones. Mars shows that oceans can vanish. Earth reminds us that oceans can also be degraded long before that happens. Mars preserves the geological memory of a world that once held substantial surface water, but gradually lost it through atmospheric escape, magnetic field collapse, and planetary cooling. Evidence from valley networks, mineral deposits, isotopic measurements, and orbital observations indicates that early Mars may have supported rivers, lakes, and possibly a northern ocean before those planetary conditions changed. This transformation demonstrates that oceans are not permanent features of rocky planets. Instead, they emerge only when a specific combination of atmospheric protection, geological activity, and climatic stability allows liquid water to persist over long periods of time. By studying how Mars lost its water, planetary scientists gain insight into the delicate balance that allows oceans to endure on Earth, a balance that remains essential for the long-term stability of our own planet's ocean systems. Across this essay series, we have followed the story of oceans from several perspectives. We began with Earth's oceans as dynamic planetary systems that regulate climate, circulate heat, and sustain the biosphere. From there, the discussion expanded outward to consider ocean environments elsewhere in the solar system, including worlds where water may exist beneath thick shells of ice. Antarctica provided a crucial bridge between those ideas. Beneath kilometers of Antarctic ice lie hidden lakes and ecosystems that survive without sunlight, demonstrating that life and water systems can persist in environments that at first appear inhospitable. Mars adds the final perspective. It preserves the geological memory of a planet that once held water across its surface, but ultimately lost the conditions required to sustain it. Today, when scientists search for life beyond Earth, they often focus on environments that resemble Antarctica's hidden lakes, or the subsurface oceans believed to exist beneath the icy crusts of worlds such as Europa and Enceladus. These environments suggest that oceans can persist even in cold, dark planetary settings. Mars reminds us of the other possibility. Planets can lose their oceans entirely. Taken together, these worlds, Earth, Antarctica, Europa, and Mars, reveal the many ways oceans can exist across the solar system. Exposed at the surface, hidden beneath ice, sealed within subglacial systems, or preserved only in geological memory. Understanding those possibilities deepens both the search for life beyond Earth and our appreciation of the oceans we still possess.